Welcome to the deep dive. Today we're going to be going on a journey into a fascinating world, the world of intelligence mathematics. Yeah, we'll be exploring some research that tries to tackle a question that's really intrigued thinkers for centuries. Can we actually define and measure something as complex as intelligence, using mathematical formulas?
It's really exciting because this research isn't just about, creating machines that just mimic human intelligence. It's about finding a universal definition of intelligence that could apply to any system, from the human brain to a computer program.
So we're not just talking about AI that can, play chess or write
Mm.
poetry. We're talking about general intelligence, like capable of tackling any problem.
Exactly. And a big thing with this idea is the concept of a rational agent, an entity that acts in the best way possible to achieve its goals in any environment. And this research is trying to capture that essence of intelligent behavior in a mathematical framework.
Okay, that's a pretty mind-blowing concept.
Yeah.
But like, is that even possible?
Well, there's this theoretical model. It's called AIXI, and it suggests that it might be. AIXI is a really ambitious idea. It draws on fields like computer science, mathematics, and even philosophy, all to create a blueprint for a truly intelligent system.
Wow, that's a lot of ground to cover. So how does this AIXI model even work? Does it define what intelligence actually is?
Well, AIXI relies on this idea that intelligent agents are good, exceptionally good at finding simple explanations for the complex patterns they see in the world. This is where the concept of Occam's razor comes into play.
Ah, Occam's razor. Right. The simplest explanation is usually the best. I use that all the time. But how does that even relate to defining intelligence?
Well, imagine you're a scientist, you're observing some phenomenon. You could come up with a very complicated explanation, an explanation that has tons of factors and exceptions. Or you could find a simpler, more elegant theory that explains those observations just as well.
Right, that makes sense. So are you saying that more intelligent agents are better at applying Occam's razor, at finding those elegant explanations?
Precisely. And it turns out that simplicity, you can actually quantify it using a concept called description length, which is a key idea in information theory.
Okay, now we're getting into some technical territory. What exactly is description length?
Think about it this way. If you want to describe a complex object or a pattern, you need a certain amount of information. A simple object can be described with very little information, but a more complex one, that requires a longer description.
So a simple shape, like a square, that could be described with just a few words, but a complex fractal pattern would need pages of equations.
Exactly. Now imagine you could describe something using a computer program, the length of the shortest program that can produce that object or pattern. That's its description length.
So are you saying that intelligence is about finding the shortest computer program that can explain the world around us?
Well, in a way, yes. This is a concept. It's called Kolmogorov complexity. The idea is that more intelligent agents are better at compressing information, at finding those short, elegant descriptions.
This is starting to click into place. But how do we actually measure this Kolmogorov complexity?
That's where things get a bit tricky. Kolmogorov complexity, it's a theoretical concept. It's impossible to actually calculate directly for most things, but it provides a powerful framework for thinking about simplicity and intelligence.
Okay, so we've got Occam's razor and description length. What other pieces of the puzzle are we missing to build this mathematical model of intelligence?
The next piece is Bayesian probability. This is a way of updating our beliefs about the world. As we gather new information, we start with a prior belief, our initial assumption before seeing any evidence.
So like a hypothesis, like we want to test.
Exactly. Then, as we observe data, we update our belief using Bayes' rule, which forms a posterior belief that takes into account the new evidence.
Okay, I see how they could be useful for like a learning agent. But how does this fit into the bigger picture of defining intelligence?
Well, imagine if we had like a universal prior, a kind of ultimate starting point for any learning problem. This prior would be unbiased and represent the most fundamental way of looking at the world.
Wait, so you're saying there could be a mathematical formula that captures the most unbiased way
Yeah,
of understanding the universe?
it's a bold idea, and it's called Solomon-Off induction. It combines Occam's razor, Bayesian probability, and Kolmogorov complexity to propose this universal prior.
Hold on, so you're saying that Solomon found a way to combine all these ideas
Yeah.
mathematically to create like a universal starting point for learning?
Yes, and it gets even more interesting. Solomon-Off induction doesn't just provide a prior. It also offers a powerful method for prediction. It suggests that we can predict anything, in principle, with increasing accuracy, given enough data and computational power.
That's incredible. So you're telling me there's a mathematical formula out there that could theoretically predict the future.
That's what Solomon induction proposes. And it's at the heart of the AI-XI model we discussed earlier. AI-XI uses Solomon induction to try and achieve optimal behavior in any environment.
This AIXI is starting to sound like something straight out of science fiction. Is it really possible to even build something like this?
Well, there's a catch. AI-XI, in its purest form, requires immense computational power, so it's practically infeasible with our current technology.
So even though we have this elegant theory, we don't have the tools to actually make it work? That's kind of disappointing.
It is a challenge. But don't worry, the story doesn't end there. Researchers are actively working on practical approximations of AI-XI and Solomonoff induction that are much more computationally manageable.
That's good to hear. So what can we do with these approximations?
We can do some pretty fascinating things. One example is something like universal search. These are algorithms that can efficiently search for solutions to problems by finding those short, elegant programs that describe them.
So instead of brute forcing every possible solution, these algorithms are trying to find like the most elegant, compact representation of the answer.
Exactly. And this aligns with the principles of intelligence we've been talking about, finding that concise and insightful way to represent information.
I'm starting to see how these abstract ideas from information theory can have real-world applications. This is really exciting.
It is. And there's another fascinating application called the minimum description length principle, or MDL. It's a method for choosing the best model from a set of possibilities. It's all about finding the model that can describe both the data and itself in the shortest, most efficient way.
So it's like a competition between models, and the one with the shortest description wins.
You could think of it that way. And this principle has applications in so many different fields, from machine learning to statistics, even the philosophy of science.
Wow, it seems like this concept of description length is really powerful. It's incredible to see how it connects so many different areas of knowledge.
It really is, and it has some pretty amazing implications for how we think about intelligence itself. Some researchers believe that the human brain, it might be operating on principles similar to MDL, constantly seeking that most compressed, efficient representation of the world around it.
That's a mind-blowing idea. It makes you wonder, if our brains are constantly trying to find the shortest computer program, that can explain our experiences.
It's a fascinating possibility. It suggests that this drive to find meaning and understanding might be connected to these fundamental principles of information theory. We're essentially trying to compress the vast stream of data that we receive from our senses, into a more manageable and understandable form.
This is all so incredibly thought-provoking. But before we get too carried away, I think we should pause here. This is a lot to take in, and I'm sure our listener could use a moment to process everything we've covered.
I agree. We've covered a lot of ground, and there's still much more to explore in this fascinating world of intelligence mathematics. We'll delve further into these concepts and their implications in part 2 of our deep dive.
Welcome back to the Deep Dive. I hope you've all had a moment to ponder those mind-bending concepts, the ones we explored in the first part, in our journey into intelligence mathematics. It's incredible to think that we might be able to define and measure intelligence using mathematical formulas, isn't it?
It really is a fascinating area of research. We've just scratched the surface of how these ideas from information theory can help us understand intelligence, the nature of it.
Exactly. And I'm really eager to dig deeper into the practical applications that you were talking about. You mentioned something called the universal similarity metric, and you said it can measure the similarity between two things based on how well they compress together. How does that even work?
It might sound a little counterintuitive, but the basic idea is if two things, if they share a lot of structure, like underlying structure, then you can describe them much more efficiently together than separately. It's kind of like, imagine you're packing a suitcase. You can fit way more clothes in there if you roll them up, and pack them tightly together than if you just throw them in randomly.
Okay, I think I'm starting to see the analogy. So if two things have, a lot of common patterns
Yeah.
or structure, they pack more efficiently in terms of information.
Precisely. And this principle has been used to develop some truly amazing applications. For example, researchers have used the universal similarity metric to group different species of animals based just on their DNA sequences.
So they can determine how closely related two species are just by looking at how well their DNA compresses together.
Yes. And the results, they've been remarkably consistent with traditional methods, the ones that classify species based on, their evolutionary relationships. It's amazing. It's a testament to how powerful this approach is
Yes.
to uncovering those hidden connections and those patterns.
This metric is starting to sound like a universal tool for understanding relationships between, I don't know, all sorts of things. What other applications have been explored?
Well, it's been used in a wide range of fields, from linguistics to music. Linguistics, researchers have used it to classify languages based on text samples. And music, it's been used to cluster pieces by different composers, just based on their musical style.
Wait, are you telling me they can identify the composer of a piece of music just by how well it compresses with other pieces by the same composer?
That's right. And what's remarkable is that this method, it doesn't need any specialized knowledge, about the domain. It works purely on the principle of compressibility, which is what makes it so versatile and powerful.
It's almost as if we're kind of getting a glimpse into this fundamental principle of how information is organized and structured in the universe.
I think you're definitely onto something there. It's like we're discovering a universal language, a language of structure and similarity, an information theory that's giving us the tools to understand it all.
This is all incredibly fascinating. But, I want to circle back to the AIXI model for a second, the one we discussed earlier. You mentioned that it, relies on Sarnoff induction to try and achieve that optimal behavior.
Right.
In any environment. But you also said it requires immense computational power, making it, practically infeasible with current technology.
Yeah.
So does that mean it's just a theoretical pipe dream?
Not necessarily. While AIXI in its purest form might be beyond our current computational capabilities, it's still a very valuable theoretical benchmark. It helps us understand those fundamental principles of intelligence, and it gives us a goal to strive for as we develop, more practical AI systems.
So it's like a blueprint
Yeah.
for a perfectly intelligent agent, even if we don't have all the tools to actually build it yet.
Exactly. It's a theoretical ideal that guides our research and helps us push the boundaries of what's possible with AI. And remember, researchers are developing those practical approximations of AXI and Solomonoff induction that are much more manageable, computationally speaking.
That's encouraging. It seems like there's a lot of promising research happening in this field. But you have to admit, all this talk about building super intelligent machines, it makes me a little uneasy. Like, what happens when we create AI that's as smart as us? Or even smarter?
I think that's a valid concern. It's definitely something to think about. As we continue developing these more sophisticated AI systems, it's really crucial that we think about those ethical implications
Yeah.
of our creations. We need to make sure that these systems are aligned with human values and that they don't pose a threat to our well-being.
I completely agree. It's a responsibility we can't take lightly. But, I also want to remember. I want to remember the incredible potential that AI has to do good in the world. We talked about its applications in medicine and sustainability, space exploration, areas where AI could help us solve some of humanity's biggest challenges.
Absolutely. AI has the potential to revolutionize so many fields and improve the lives of billions. It's really up to us to make sure that we develop and use this technology responsibly and ethically.
It's inspiring to think about what we might be able to achieve if we can really harness the power of AI for good. But before we get, too carried away with all those futuristic visions, I think it's time to bring our deep dive back down to earth for a moment and focus on, the here and now.
I agree. We've explored some incredibly complex and abstract concepts, and I think it's important to, to reflect on what all of this means for us as individuals.
Exactly. So for the final part of our deep dive, let's turn our attention to the human element of intelligence and explore how these mathematical ideas can enrich our understanding of ourselves and our place in the universe. Welcome back to the deep dive. We've been on this crazy journey exploring this world of intelligence mathematics from like abstract theoretical models to some pretty mind-bending applications. Now, this last part, I want to shift our focus a bit to the human side of all this.
Yeah, I think that's a crucial perspective after all. We're talking about mathematical formulas,
Yes.
right? And algorithms and all that. But the ultimate goal of this research is to understand intelligence, something that we, as humans, we experience it
Yeah.
in a very personal and profound way.
Exactly. And I think that's what makes this whole topic so captivating. It's like we're using these tools, the tools of mathematics, to try and unravel one of the greatest mysteries of existence. What does it even mean to be intelligent?
It's a question that's fascinated, philosophers and scientists
Yeah.
for centuries. And now with artificial intelligence and all that, it's even more urgent. It's not just about understanding our own intelligence, but it's also about creating new forms of intelligence in machines.
That's a really important point. It's almost like this research is holding up a mirror to ourselves
Hmm.
and is making us confront, like, what makes us uniquely human?
Hmm.
If we can define intelligence in a way
Mm-hmm.
that applies to both humans and machines, what does that say about, about the nature of consciousness,
Hmm.
creativity, all those qualities that we think of as being human?
It's a profound question, and it doesn't really have, easy answers, but I think just exploring these ideas can help us appreciate the complexity
Mm,
and the beauty of our own minds, even as we're trying to create new forms of
I
intelligence.
totally agree. And one of the most compelling ideas that we've
Yeah.
talked about is this idea that intelligence, it might be connected to this ability to compress information,
Mhm.
to find like the shortest, most elegant explanation for the world around us.
It's a very powerful concept, and it makes you wonder, if our brains are always looking for these compressed representations of reality, is that what gives us this sense of meaning, this understanding? Are we, in a way, just trying to create the most beautiful and concise code, a code that can capture our experience?
That's a beautiful way to put it.
Yeah.
It connects to something you said before, this idea that the human brain might be working on these principles,
Yeah.
similar to the minimum description length principle,
Yeah.
always trying to find that efficient way
Yeah.
to represent information.
Yeah. And it's not just about efficiency. There's also an element of elegance to it
Yeah.
and beauty. Like think about like a skilled artist.
Right.
They can capture like the essence of a scene with
Yeah.
just a few brush strokes, or like a musician can evoke all these powerful emotions with a simple melody.
Those are great examples. It's like they're finding the most compressed representation of an idea or of an emotion,
Yeah.
distilling it down to its purest form.
Exactly. And it makes you think, does this drive for compression, this need to find elegance and beauty in the world? Is that a fundamental part of what makes us human? Maybe it's what drives, our creativity,
Yeah.
our curiosity, our constant quest for meaning.
I think that's a really profound insight. It's like this search for understanding. It isn't just about accumulating knowledge. It's about finding that most elegant and that most beautiful way
Yeah.
to represent that knowledge. It's about, finding the patterns, the connections, the underlying structure that gives the world meaning.
And maybe that's where the real power of intelligence lies, not just in, processing information, but in finding the beauty and the meaning within it.
That's a wonderful thought to leave our listener with. We've covered so much in this deep dive, exploring these complex ideas from information theory to AI, even philosophy. But I think the biggest takeaway here is that this quest to understand intelligence, it's really a quest to understand ourselves as a journey of discovery. That takes us to the very heart of what it means to be human.
I couldn't agree more. And we may never fully unravel the mysteries of intelligence, but the very act of exploring these questions, it enriches our understanding
Hmm.
of ourselves and the universe that we live in.
Thank you for joining me on this fascinating adventure, and thank you, listener, for diving deep with us. We hope this whole exploration has sparked your curiosity and inspired you to keep thinking about these wonders, the wonders of intelligence, both human and artificial.